Hey guys, this week I'll be doing an example problem showing you guys how to use the equation of motions to solve for a typical uh, dynamic stability problem. As you already learned during class, there would be a total of 12 equations would completely describe the motions of an aircraft. That is the sixth equation of translational and rotational dynamics, as well as six equations of the Euler rotational and translational tracking. That is to describe the path of a moving object. So today, assume you have an aircraft in a wind tunnel, undergoes only in pure vertical motion, and there's no rotation for that model. You are given the wind tunnel velocity, the weight of the aircraft model, the wind area of the models, the CL alpha, as well as the air density inside the tunnel. And you are asked to determine the vertical translation of the aircraft, the rate of vertical translation of the aircraft, given the initial conditions. So how do we start this kind of problem? First of all, if you read the problem, it said that the aircraft only experience a pure vertical motion. That is, the aircraft, in other words, is constrained in pitch. And so since the aircraft is constrained in pitch, you can write out the equation of motion for that aircraft. And that is, I'll just write out the whole thing here and I'll explain it to you later. Okay, so since our aircraft is constrained in pitch motion, there's only three terms that can describe the motion of the aircraft. That is the rate of vertical translation, the rate of horizontal translation, as well as the pitch rate of the aircraft. Okay, and if you look at the 12 equation of motion that was given to you during class, you can just rewrite them all, which terms corresponding to the matrix, the given matrix. And we also given no rotation rate for the aircraft. So since there's no rotation, the Q is going to be equal to 0. And so you can rewrite this equation, the whole equation, as only two terms, that is in horizontal and vertical translation. See, it's going to be G over W of Fxb plus G over W of Fzb plus G. Okay, since Q is equal to 0, you are left with U dot and W dot. So if you move the W over G term to the other side, Q equals 0, all of these go away, you are left with the Fsb and the weight. And that is how everything is written right here. And because you are asked to determine the rate of vertical translation, W dot. So the W dot in this case, that is with respect to time, it's going to be right here, that equation. So that is G over W times FZB plus G, the gravitational constant. And that term FZB in a aircraft that only experience a vertical motion, we have the FZB is going to be equal to the negative of the lift force acting on that model, and the negative lift is going to be equal to the lift formula is just CL times QS. Q is the dynamic pressure inside the tunnel, and when you rewrite this equation, it's going to be negative of alpha CL alpha times Q times S. Well, so if you still remember, when the aircraft undergoes a motion in U and W, the angle of attack alpha is going to be a tangent of W over U, and we use the small angle approximation. It's just going to be W over U. So I can rewrite this equation as negative of W over U times CL alpha time, I'm just going to write out the dynamic pressure, that is half rho U square times S. U is going to be the velocity inside the tunnel, which is the air velocity inside the wind tunnel, which is given right here. And so if you put in all the numbers, except for W, you don't know the W yet, it's just going to be W with respect to time CL alpha divided by U times half rho V square times the area, and this gonna turn out to be negative 72.03 omega t, which is the translation in vertical direction. And so if you put the FZB term back into the equation, you're gonna have the W dot T is gonna be equal to negative 72.03 omega t times 9.81 divided by 40 plus 9.81. This is gonna turn out to be negative 1767 WT plus 9.81. I can rewrite this equation as plus 7. And if you realize this is just a linear first order linear differential equation, this equation is going to have a general solution of Wt equal to C1 e to the gamma t plus C2, and if you solve for this equation, it just gonna be C1 times e to the negative of 17.67 t, okay, plus 0.56. And so now it's time for us to use the initial condition given by the problem. So if W0 at time equals 0, just going to turn out to be C1 plus 0.56 will be equal to 1. And the constant C1 turn out to be 0.44. And so the general final solution for our problem just gonna be 0.44 e to the negative 17.67 t plus 0.56. Alright, so this is one of the standard steps that you need to remember in order to solve for a equation of a motion of aircraft. So you first need to determine what constraint in motion does that aircraft have. So in that case, you can write out the system of equation and now apply for one of these given, like in the problem, like no rotation or pitch constraint and so on, in order to simplify that system of equation. And from that point, you should be able to solve for a particular motion of aircraft using the learned knowledge during this class and previous class. All right, thank you so much for watching, guys. Good luck with that.